All right, let's do this. We have just finished talking about this discrete random variable, making that probability distribution so that then we can do the mean and standard deviation, and which then allows us to do some continuous probability from that discrete event. Okay, but let's do a couple of quick examples, basic ones of just filling in this, finding some probabilities, and also practice that in your calculator stuff. So here we go. Your page looks like this, where we're going to just do some basic stuff here. We've got these numbers from 77 to 81. We don't have context here. In example 2, there is context. Okay, so you want to find this missing probability here first. Find the probability of 80. Well, hopefully you remember that all of these probabilities add up to 100%. So then, because of that, you can determine what's missing there. Okay? So I'm going to you to take a few minutes and see if you can compute all of these ideas here, including getting that mean and the variance. Interesting. Not the standard deviation. But the calculator just gives you the standard deviation. Well, what are you going to do if it asks you for variance and not standard deviation? Well, the calculator gives you standard deviation, but we know we just need to take this standard deviation it gives us, square it, and then we'll have the variance. Okay? All right. So pause the video, think about these answer choices, and then we'll come back and see how you did. All right. Let's see how you did. Here we go. All of those add up to 60%, leaving 40% left for 80, for the 80. All right. Then, so greater than 80 is just this 10%. Less than or equal to 80 is all of the other part except that 10%. Okay, so remember how to do this in your calculator. I went to list 1 in my calculator, put in those top numbers, and list 2 was the frequency, and I put in those bottom numbers. And now, if you had a older calculator that did not have the stats wizard menu, remember you could do second calc of list 1, second L1, comma, second L2 for the frequency, and then that'll give you the answer. I have older data in here, so this was the data from the card game earlier. Okay, but I put a video there. If you do not have the stats wizard menu, how to handle that. Okay, and then remember that it gives you the standard deviation, not the variance. The standard deviation was 1.24. Therefore, I'm going to square it to get the variance. Okie dokie. Next one is contextual. So it's talking about the hamster and how many live births are born to the mama and so on and so forth. Okay, so take a few moments, pause the video, try these problems here, and then we'll get back together and see how you do. Pause and try these. All right, let's see how you did. So the missing probability here was 10% because all the others added up to 90. So the missing one was 10% for live baby hamsters, which I guess are called pups. All right, 5 to 7, see, so you're just going to add up the 5, the 6, and the 7 probabilities. All right, and then at least 6. So at least 6 is 6, 7, 8, and 9. So I added those up. And then the mean and standard deviation, I asked you to do that, I guess, all in one fell swoop. Oh, look, I didn't put the standard deviation there. Yikesies. Okay. So hopefully you computed what that standard deviation was. So the mean was 5.8. So I'll have to go back in there and fix that. Interpret the mean in context. Okay. So remember how we had done that with my winnings. Remember, we needed to say in the long run, and we needed to say what's expected to happen on average. Okay, so here we go. So that being 5.8, of course, the mama cannot have 5.8 baby hamsters. Okay, we're not talking about parts of hamsters here. But in the long run, after many, many litters, then this breeder expects his female hamsters who were over 12 months old and haven't had a litter in the past 6 weeks. Okay, so anyway, there was some criteria there to have 5.8 live baby hamsters, live pups on average per birth. Okay, per birthing situation or whatever. Okay, so I use in the long run, this is what's going to happen on average. And then, of course, my context. Okay. All right, very good. So now let's move on to the next part. Here we go. So now you're going to get to practice doing some of those probability distributions. Okay, it's important that you are able to come up with these tables of probability values on your own. Okay, so let's take a look at these. Here we go. So a fair coin is tossed twice. Okay, list all the possible outcomes for 2 tosses of the coin. So I hope that you can tell that when that happens, you're going to have 1 or 2 tails. Okay, so here's what's going to happen. You're going to have 2 tails, or you're going to have a tails and a heads, and then a heads and then a tails, and then heads, heads. Okay, so there's the possible outcomes. Now, here's a graph of that, by the way. So take a look at this. Let X be the number of heads in the 2 coin tosses. Create the probability distribution for the X. Well, the possibilities are 0, 1, and 2. Okay, because that's 0 heads, 1 heads, 2 heads. Now, how frequently do those happen? What's the probability? Well, 1/4 of the times you have 0 heads, 2/4 or a half, you have 1 heads amongst the 2 coin tosses. And then 1/4 of the time you have 2 heads. Okay, so then I went and I put that into my calculator. Okay, now there's only 3 things here. So you have to show the formula written out, and then you can go to your calculator. I usually do like to go to my calculator because of the standard deviation one. The standard deviation one is a pain in the patootie. Sometimes the mean is not too bad, but the standard deviation is. So I generally always just go put it in my calculator. So make sure you showed this work. The the x value times its probability plus the next x times the probability and so on. And then my calculator gave me 1 standard deviation. Here's my work shown. Now, technically, you could have just put plus dot, dot, dot and not shown this middle term. Okay, but it's only 3 terms, so I guess I showed it. So it was x minus the mean quantity squared times its probability plus the next x minus the mean quantity squared times its probability, and so on. And that came out to 0.71. Okie dokie. Let's see the next situation. Here we go. So this is a pair of die that are being rolled. Okay, so we're going to roll the 2 die. Ooh, I got this thing right here, and look, I can set it to just roll 2 dice. So here we go. We're going to roll a pair of die, and that would I would list that as 3, 4. So that's one of the things that this talks about is that we're going to represent 1, 2 to be a 1 on the first roll and a 2 on the second roll. So in my case, it's 3, 4. So this would look like 3, 4, but yet the sum up here, the sum is 3. For me, the sum is 7. Okay, so that's kind of the notation they are using. So you can see here, look at how they completed this or had this written out. Okay, so first we've got this here. So see, I went ahead and I included these for you. See this 1, 1, that doesn't mean 11. This 1, 1 means a 1 on the first die and a 1 on the second die. So what's the sum of that little piece right here? The sum of that is 2. Okay? Then look at these. What's the sum of those? The sum of those are both 3. Okay? Then we've got this. There's 3 different ways you can have a sum of 4, and so on. Okay? And so here we go. So then that made our possible sums be this. The sum, x is the sum of the dots on the top of 2 die. So I can have a sum of 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, all the way up to 12, because that's what that 6 plus 6 is. Now, how often is that happening? Well, a sum of 2 was only happening 1 out of 36 times. A sum of 3 is happening 2 out of 36 times, and so on. 4 happened 3 times. A sum of 5 and so on happened 4 times, and 6 and a sum and so on. And you know that you can tell it's going to then go back down. So here is what the probability distribution looks like. Okay, so now we can do the mean on average. What do you expect the sum to be? And with what standard deviation? So here we go. Let's look at the work that has to be shown. And then we can go to our calculator and do all one variable stat stuff. Okay, so the mean is the expected value. Look what I did here. Because I have the table shown, my work can just be the first in the sequence up to the last in the sequence. Okay, so I've got 2 times 1/36 plus dot, 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 all this in the middle. And then the last one, 12 times 1/36. Okay, and then I went and put that in my calculator. So on average, that sum is going to be 7. Let's just think about this. Have you ever played craps in poker? Guess what? You crap out, meaning you lose all your money that you bet if you hit a 7. Guess what happens? What sum happens most frequently? Look right there. The sum that happens most frequently is 7. Boom, boom, boom. You see, the casinos know the probabilities. All right. I don't know the exact rules to that game craps, but I know that you crap out if you get a 7 or a sum of 7. Okay, anyway. And here's the standard deviation, but notice I did the x minus the mean quantity squared times the probability plus up to the last one. Okay, that came to 2.42. All righty then, here we go. So using this table up above, answer these questions. Greater than or equal to 9, so I'm just going to add those all up together. Ooh, looky here. Love it, love it. I forgot that I put this in here. So now we're going to do the normal approximation to this discrete situation, a continuous probability of this discrete scenario. So now look at what happens. I ask you to use this mean and this standard deviation to compute the probabilities based on x being greater than 8.5. So let's think about that for a second, because let's take a look at this picture. That might help you. Look at this picture. Okay. See this picture here? This is all of the sums. Okay. So look at this 9 up to 12. Look at where the start of that 9 bar is. It's halfway between the whatever that is. It's halfway between 8 and 9. So by like discrete wise or binomially or whatever, I can add together these 4 bars, okay, which is what we were doing when we added together these 4 probabilities, okay? But if I was to do the normal model, okay, if I was to do the normal model, then I'm actually going to be computing the area from 8.5 to infinity. Okay, so that's what I do here. I'm a normal model with a mean of 7 and a standard deviation of 2.42 that I got up in parts A and B. X is 8.5. X minus the mean over the standard deviation is this z-score of 0.62, and then I'm going to norm CDF that, and I get 0.268. Look, and so then that's what we're interested in. How close are those? We want to know, how well did the continuous approximate the discrete? And there we have it. I mean, they're within 1 percentage point. So, and as your bars get smaller and so on, that will even get closer approximation. Okay, interesting, interesting, interesting. And so I think that I'm going to stop right there because this problem is quite involved, and I may not even have class time to go over it, but I'm going to probably ask my students to watch this for homework if I don't have time to go over it in class, because it is a really important question. It was a problem number 6 on the AP test. And so I want to talk to you about that. That's actually one of the it is the most heavily weighted question of the free response section. So this one particular problem would be the most heavily weighted problem towards your points. And so, anyway, and it's also kind of an out of the box thinking. It has things that are in the box, but it also then has things outside of the box. So, I'm going to do a separate video for this one, and that you can look at on your own time as you have available.